Hello everyone, welcome back to this channel. In today's video, we are going to start with a discussion on partial differentiation. So let us begin by understanding what is partial differentiation and how it is different from ordinary differentiation. So suppose you have a function, say y, which is a function of a single independent variable x. That means y changes as x changes. Y depends on x. X is the independent variable and y is the variable which depends on x. So this will be called the dependent variable. So obviously, since y is a function of x, it's going to change as x changes. So the rate of change of y with respect to x is captured via the derivative of y with respect to x, which is denoted by dy by dx, or sometimes as y1 or y dash. So y dash in a way captures the rate at which this dependent variable changes with respect to the independent variable x. Now in the real world situations, generally a function is not dependent on a single independent variable but a lot many independent variables. For example, to be very simplistic, let us consider a rectangle. We know that the area of a rectangle depends on its length as well as breadth. So area is a function of L and B both. So this is the most simple extension of a one variable setting to a two variable setting. So the rate of change of area can be captured with respect to change in length as well as change in breadth. Similarly, there are other things. For example, the weather of a particular city depends on so many factors, right? Similarly, your result in some class test or some examination depends on the amount of hard work you put in, the kind of teaching resources you have got, the kind of mentor you have got, the kind of the level of the paper, your mental stability during the examination time, and a lot many more factors are there. So in a real world scenario, whenever you capture change, it's captured with respect to a lot of variables together, and that is when partial differentiation comes into picture. So suppose f, instead of being a function of a single variable x, suppose my z, let's call this as z is a function of two variables x and y, or to be more general, we can say f is a function of more than one, say x1, x2, x3, x4. It's a function of four variables x1, x2, x3, x4, where all of them are independent. They do not change with respect to each other, but z depends on all of them individually. So we can capture the rate of change of z with respect to x1, with respect to x2, with respect to x3, with respect to x4 separately. So that is when the notation del comes into picture, and we talk about the rate of change of z with respect to x1. And when we talk about this rate of change is called the partial derivative of z with respect to x1. And while we differentiate z partially with respect to x1, all other independent variables are treated as constants. For example, suppose my z is x square plus y square. Then z is changing with respect to x, z is changing with respect to y. X and y are two independent variables on which the dependent variable z is depending. So I can talk about del z by del x. While doing del z by del x, I mean that I am differentiating z partially with respect to x. So please keep in mind there is a notational difference also. There is a difference between the d notation and the del notation. D notation is used to capture the derivative in an ordinary setting. That means your function is dependent on a single independent variable. Whereas this del notation is reserved for partial derivatives, meaning thereby that there are other independent variables also which are treated as constant while you are differentiating partially with respect to x. Your y will be treated as constant. So you'll simply differentiate this partially with respect to x, treating y as a constant. So your del z by del x is going to be 2x. Similarly, your del z by del y is going to be 2y, and so on. So this is how you talk about partial differentiation, and that's the more relevant notion in mathematics, because change is the law of nature and change we know is captured via derivatives, but the change in the real world situations is not happening because of one single independent variable. There are many factors which are affecting the change, and that is what makes partial differentiation more relevant to the real world problems than the ordinary ones. So let us begin with this formal definition of partial derivative. Suppose z is a function of more than one independent variable. Say z is a function of x, y, or we can say x1, x2, x3, or we can extend this definition to n independent variables also. Then del z by del x, or the notation for this partial derivative is z subscript x. This means the partial derivative of z with respect to x. When we say partial, we mean that the other variable is a constant. So while doing differentiation partially with respect to x, your y will be treated as a constant. Similarly, we can talk about del z by del y, for which the notation is zy. This is the notation zx or del z by del x. This is the notation zy or del z by del y, which means differentiating z partially with respect to y. And when we say partially, the other variable will be treated as a constant. So when you're doing differentiation partially with respect to y, x will be treated as a constant. When you're doing it with respect to x, y will be treated as a constant. And in a three-dimensional setting, suppose you're talking about del z by del x1, then you'll differentiate with respect to x1, treating x2 and x3, both of them as constants. So whatever you are differentiating with respect to in partial differentiation, only that change will be captured. Other variables will be treated as constants during that partial differentiation. Now there's a point to note here that in general, if your z is a function of xy, then del z by del x, which is the partial derivative of z with respect to x, is again a function of x and y. Similarly, the first order partial derivative del z by del y is also a function of x and y. For example, suppose my z is, let's say, x cube plus xy square. Then my del z by del x will be 3x square. I am differentiating partially with respect to x. So y is like a constant. So I'll treat y square as a constant. Derivative of x is 1. So this is my del z by del x. You can see that this is again a function of x and y both. So I can do partial differentiation of del z by del x also with respect to x. When I do with respect to x again y will be treated as a constant. So this will be 6x. But I can differentiate this del z by del x with respect to y also, because del z by del x is a function of x and y. So when I do that, 3x square will be like a constant, so my answer will be 2y. So that's how every level partial derivative splits into how many further levels as is the order of the independent variables. How many independent variables are there? It's going to depend on that. So if z is a function of two variables, then del z by del x and del z by del y will be the first order partial derivatives. The second order partial derivatives will be obtained by differentiating del z by del x and del z by del y with respect to x and y again. Now when we do del z by del x with respect to x, we get zxx, which means differentiating z partially with respect to x twice. Zxy means we differentiate del z by del y with respect to x. Zyx means we differentiate del z by del x partially with respect to y. And zyy will mean we differentiate del z by del y again with respect to y. And for all practical purposes, these two partial derivatives will come out to be the same in whatever problems we are going to consider. So the cross derivatives are equal for most of the questions, but they're not equal in general. But yes, for most of the questions that you are going to encounter, you can take the derivative in any order you feel like, whether you differentiate with respect to x first, y later, or the other way around, your answer will be the same. So these two cross derivatives will be equal for you. So this is called cross derivatives. These are called pure derivatives. When you are differentiating with respect to the same variable again, it leads to a pure derivative, because the independent variable is a single independent variable on which everything is depending. And this is also a pure derivative with respect to y. So these are the four second order partial derivatives. Similarly, del 2z by del, now this is again a function of x and y, so you can further differentiate all four of them to get 8 third order partial derivatives. So you can see that the number of partial derivatives that you get at every step is going to be 2 to the power n if 2 is the number of independent variables, like that. So the chain goes on like that. So partial differentiation is nothing but normal setting differentiation, only treating the other variables as constants for the time being. And if z depends on more than one independent variable, please keep in mind that this d notation is not to be taken for the partial derivative. It's reserved for ordinary derivatives only. Del is the notation that you have to take for partial differentiation. So now let's look at some examples on partial differentiation. Look at the first example. Suppose z is a function of x and y, which is given like f of x plus ay. A is a constant here. So suppose z is given to be some function of x plus ay plus some other function of x minus ay, and you are expected to show that zyy is a square zxx. Now this is primarily going to depend on partial derivative of z with respect to y done twice and with respect to x done twice. Now to reach that level, you will first do partial differentiation with respect to x. Now keep in mind that when you are differentiating partially with respect to x, y is like a constant. So this ay appearing inside f and phi, they are like constants. So it's like z is f of x plus 2, something like this, plus phi of x minus 2. So something constant is appearing here when you are differentiating partially with respect to x. So what will be the derivative? It will be the derivative of f into the derivative of x plus 2 with respect to x, which is 1. So we don't write anything here. Similarly, the derivative of phi with respect to x into the derivative of x minus ay with respect to x, which is 1. So using the chain rule, simply you get zx is equal to this. That's the partial derivative of z with respect to x. Now one more differentiation of this partial derivative with respect to x again is going to give you the second order pure derivative zxx. Now once again, using the same logic, you will differentiate this partially with respect to x. You will land into f dash will become f double dash into the derivative of x plus ay. Again, it's a 1 plus phi double dash x minus ay. So that's what you get as the answer to zxx. Now the question wants you to show that zyy is a square zxx. So let's calculate zy now. Now when we do zy, x is like a constant. This x is like a constant. So you have to treat your function as some constant. Let's say phi plus ay plus phi of phi minus ay. It's something like this, which is to be differentiated with respect to y. So when you do that, it's going to be partial derivative of z with respect to y will be the derivative of this into the derivative of 5 plus ay with respect to y. So the constant a comes out using the chain rule. Similarly, here the derivative of phi into the derivative of 5 minus ay, which is minus a, because you are differentiating y with respect to y this time. So this is what you get as your partial derivative of z with respect to y, the first order. But in the question you want second order. So let's do zyy. So one more differentiation, one more a comes into picture, dash becomes double dash, and here minus a comes again, so makes it a square, and dash becomes double dash on differentiating once more with respect to y. So if you look at 1 and 2, it is easy to see that you have got what you wanted to prove. Look at what we wanted to prove. Zyy is a square zxx. So you can see from 1 and 2 easily that zyy is nothing but a square zxx. So that's how you can prove problems based on partial differentiation very easily if you know ordinary differentiation well. Because partial derivatives behave like ordinary derivatives only. You just have to keep in mind that while you are differentiating partially with respect to one variable, rest of the independent variables will be treated like constants, and you do your normal differentiation rules to establish whatever relationships are given to be established in the question. So let's look at one more question. Yeah, so in this question, u is given to be a function of x, y and z. So there are three independent variables, x, y and z, on which u depends. The question is to prove that the sum of the first order partial derivatives del u by del x, del u by del y, del u by del z is twice of u. Now it's an easy question. You just do del u by del x, treat this as a quotient of two functions of x, and straight away apply the quotient rule, keeping in mind that y and z are constants right now. When you're doing del u by del x, y and z are like constants. So you get del u by del x as this. And since it's a symmetric one, u is a symmetric one in x, y and z, so you don't have to calculate again. You can similarly on the same lines write your del u by del y and del u by del z, just simply wherever your x, for the x, e to power y plus e to power z was coming into picture. This is all symmetric, so these terms will come as it is, and here instead of, when it was with respect to x, it was e to power y z coming here. So with respect to y, e to power x, e to power z will come. Similarly, del u by del z, for del u by del z, e to power x, e to power y will come. And when you add them together, e to power x plus y plus z upon e to power x plus e to power y plus e to power z square comes out, and you are left with twice of e to power x plus e to power y plus e to power z, which cancels, 2 comes out, and you can see that it's nothing but, this was your u given in the question, so it's 2u. So very easy to establish such relationships for partial derivatives if you understand the idea that partial differentiation means differentiation with respect to this variable under consideration using the same differentiation rules as you have in ordinary setting, keeping in mind that the other independent variables are to be kept as constants whenever you are differentiating with respect to one. Only that one is changing. Rest of the independent variables are to be treated as constants. So moving on, a similar question, u is dependent on x, y, z, and you have to find the value of del 2u by del x square del. And since it's a symmetric relationship, it's always advisable to find out one and write rest of them using the symmetry of u. You don't have to calculate them again. So look here, since you have got del 2u by del x square after applying quotient rule, etc., it turns out to be this. So you don't have to redo for del 2u by del y square and del 2u by del z square. U being a symmetric function in x, y and z, you can copy the result that you get from del 2u by del x square, just replacing x by y for del 2u by del y square and x by z for del 2u by del z square, and then adding, you simply get the answer as 2 by u. Another similar question, very easy to prove again. U is a function of r and r is a function of x, y, z. So u is primarily a function of x, y, z related to x, y, z via r. So when you do uxx, chain rule will be applied because u is a function of r. So when you do partial differentiation of u with respect to x, u is f of r, and f of r is a function of x, y, z, so it's basically this. U is given to be this. So when you do ux, it's going to be f dash r into del r by del x, where del r by del x can be easily seen to be x by r from this relationship given to us. So ux is simply obtained by partial differentiation and an application of chain rule, and when you want duxx, you need to differentiate once again with respect to x. So it's like a product of two functions, so product rule has been applied here. X by r as it is into the partial derivative of f dash r, which means f double dash r into del r by del x plus f dash r as it is into the derivative of x by r, for which quotient rule has been used. So once you get your uxx, these calculations are elementary to verify. You don't have to do it again for u by y. You can use the symmetry of u to write your u by y, uzz, after replicating what you have got for uxx, and then adding and simplifying, you land into the final answer. So you can take screenshots of all these questions and practice, try to evaluate these sums on your own and match the right inside. They are not bad questions, very easy calculation wise. The only thing that one needs to understand is the idea that partial is similar to ordinary, all the rules are parallel. Just keep in mind that when you're differentiating with respect to x, partially treat y and z as constants. Rest of it is usual. So you can look at this question also. It's a similar question, very important, comes very often in most of the exams. So del v by del x is this. So del 2v by del x square on simplification leads to this. And again, using symmetry, you can just replace x square by y square for del 2v by del y square. Replace y square by z square for del 2v by del z square, add all of them together, simplify, you will get the right inside very easily. Now look at the sixth question for this video is, suppose u is again x, y, z setting, u is a function of three variables and this notation needs to be understood. This means that you are doing del by del x plus del by del y plus del by del z of u, which means del u by del x plus del u by del y plus del u by del z. But there's a square here, so that means whatever answer you get for del u by del x plus del u by del y plus del u by del z, that needs to be operated again. So suppose this final answer is, let me call it as v or something, then we need to do del v by del x plus del v by del y plus del v by del z again, because it's a square of this operator. So you'll first apply it once to u. Whatever answer you get after simplifying, you'll apply that operator again. This is a square of the operator del by del x plus del by del y plus del by z, del z, which means del u by del x plus del u by del y plus del u by del z, and whatever answer you get, you will again do, suppose v is that answer, then you will do del v by del x plus del v by del y plus del v by del z and prove that it's equal to minus 9 upon x plus y plus z whole square. So I've written all the calculations, all the steps nicely here. You can take screenshots of the solutions, try to prove them yourself and match the final answer. But if you get stuck anywhere, you can check in these calculations. When you do del u by del x, when you do del u by del y, when you do del u by del z, you add them. It's very easy to simplify del u by del x plus del u by del y plus del u by del z, because this is just, you know, your function is log. So del u by del x is 1 upon this expression into the derivative with respect to x. So that's your del u by del x. Del u by del y written similarly, del u by del z written similarly. When you add all of them, then it simplifies to 3 upon x plus y plus z, because this is a formula. X cube plus y cube plus z cube minus 3xyz is nothing but x plus y plus z into x square plus y square plus z square minus xy minus yz minus zx, which is appearing in the numerator with the 3 attached. So we take 3 out, everything cancels, you are just left with 3 upon x plus y plus z, and this is your v that you have got, because the operator was a square operator. You have just applied this operator once right now. Del by del x, del by del y, del by del z, you have applied to u, but this was a square operator. So whatever answer you are getting to this applied once, you have to apply this operator again, and that application leads to the final result, which is expected to be proved as per the question. The question is stating what you need to prove, so you can very easily get it if you do not make any calculation mistake. It's a very easy problem, and yes, here you will need to simplify, otherwise things will remain very complicated if you apply the operator here. So please simplify using the formula here before you apply the operator second time. Now this is another problem, and another interesting problem. U is log tan x plus tan y. You have to find the value. It's very easy. You just find del u by del x, del u by del y. Consider this expression. It simplifies using simple formula. Sin 2x is 2 sin x cos x. It becomes twice of the denominator and the answer turns out to be 2. So please try these questions on your own. Another problem on partial differentiation, very easy to prove again. So you can take screenshots if required. You can match your, first please do these questions on your own. Do not look at the solutions. But if you get stuck at any step, I've written all the main steps here for you to tally your answers, and there are some practice questions also given in this video for you to practice more on partial differentiation and feel comfortable about the idea of partial differentiation. So you can take screenshots of these questions. Here it's a 2 proof problem. Here the answer will be 2. So I've tried to give you the final answers also. Still, if there is any problem anywhere, you get stuck, please put your doubt in the comment section and we would love to resolve your queries. That's all for this video. In the next video, we are going to start with homogeneous functions and Euler's theorem for partial differentiation. If you like this video, please press the like button and share forward. Thank you so much for watching.